So let's take this water tank experiment a little bit further, shall we? So we'll look for dynamical balances because we are here to try to derive the equations of motion by adding rotational effect to the non-rotational equations we already derived, right? So here is looking at the tank. There is the plug in the middle, let's say, and we have the radius of the tank of r, and we have defined a coordinate here, let's say, as longitude and latitude, and there is a radial direction and a tangential direction, right? So you can think of this as latitude theta. We'll blow this into a sphere and try to understand things in the same framework by adding complexities of a spherical body on which we are rotating. Okay, so there is a radial velocity and there is a azimuthal or tangential velocity, right? That's fairly straightforward. And the tank, looking at it again, had this drain in the middle and it's rotating at some rate omega, which is given here as omega rpm. We said 5 and 10 for the two visualizations we saw. There is a pump here which is pumping the fluid into the system carefully with the diffuser to avoid creating a lot of chaos to make up for the fluid that's falling out, right? So from a non-rotating framework, so if you're standing outside in the lab and looking at the tank, then the net velocity, the total velocity, is going to be a sum of these two in a vectorial form, right? So v theta is v theta plus omega r. Okay, so there is a rotation of the tank itself and there's a rotation of the fluid. Okay, when they're in solid body rotation, they will be moving at the same speed. So you can settle the tank for a few days, make sure it's completely quiet, and then slowly start the rotation. Not if you start rapidly, obviously the tank goes first and the fluid falls behind and so on, but carefully done, you can make the entire fluid move with the tank as a solid body, which is what is done in most of these experiments, as we will see. Okay, so trying to write the vertical force balance here. This is the vertical at any given distance r. So r1 is the radius of the tank, r is the distance from the axis of rotation. The height is hr of the water column, which is obviously going to 0 at the middle. So pressure here is rho g times h minus z. When we did hydrostatic balance, we said the pressure at any point is equal to the weight of the air above, right? So we are doing exactly something similar here. So height z is, let's say, from here to there, and the fluid column is h minus z. So rho g times h minus z is going to give us the pressure. Again, this tank is shallow enough, there are no significant vertical motions, so we are still assuming a hydrostatic balance. So hr here is the height of the free surface, where pressure is actually equal to the atmospheric pressure, but for our relative calculations we can just set it to 0 because it's the same on the whole tank, right? So the simply set p equals 0 makes life a little bit easier for deriving the equations. Fairly straightforward. Just look at it again, make sure you understood it. It's not at all complicated. So when the rotation is sufficiently large, the radial velocity that the particle would feel divided by the azimuthal velocity it is going through is much less than 1. That is kind of the looking from outside into the as a non-rotating framework. Okay, so the radial balance in a non-rotating framework then basically becomes the centrifugal force flying you out, v theta squared over r, equals 1 over rho dp dr. Okay, pressure is varying radially. It's trying to hold you in. It depends on it's not linear because this surface is curving, right? So v theta squared over r equals 1 over rho dp dr. I hope I said it right before. V theta squared over r equals 1 over rho dp dr. This is the radial balance. I think you know what happens on a rotating framework, except maybe you're used to putting something on a surface and seeing it fly out with a centrifugal force or balanced with friction, etc. We'll see that example a little bit later on. Here we're talking about a fluid. Each particle is experiencing a radial gradient of pressure because this surface is corresponding to dpdr, and there is a v theta which is going to determine its net centrifugal force. Okay, we didn't do any detailed derivation, but this is fundamental physics at the very low level. So we'll come back in the next podcast and look at the details of how we will do this, how we will take this further. But I want to make sure that you understood this much. Okay?